Hi class, so we're going to go over lesson 3, modeling exponential growth and decay, and this includes half-life and doubling time. So in our last lessons, we kind of just learned about how different exponential models can be made. So we made our graphs, we learned what an exponential function is, what the base function is, and so today what we're going to be doing is we're kind of just going to be applying this to real life. So by the end of this, I forgot to point out, your homework is posted here. Again, it's on Google Classroom. Both pages both sections are in one worksheet, so you can just work through those together. So it says modeling exponential growth and decay. More importantly, we're going to be talking about half-life and doubling time. So what you're going to be able to do by the end of this class is you're going to be able to tell the difference between growth and decay by just looking at a graph or an equation. You'll be able to determine whether equation is exponential growth or decay by looking at the growth factor. You'll know the basic equation for half-life and doubling time, and you'll be able to apply equations for half-time and doubling time to various real-world application problems. So this is more of the application part of our unit. There's many real-life applications that can be modeled with exponential growth or decay. When we move on and we actually discuss and we start talking about financial or finance rather, when we start talking about investing, about debt and how that works, we're actually going to be talking a lot about exponential functions because they're often exponential. If we look at the COVID curves, all the COVID curves are also exponential functions, and they kind of flatten out. So they kind of do eventually flatten out, but that's because of something we're doing. And yeah, so we're going to be talking a lot of half-life, like a lot of things in science, bacterial growth, how we date our carbon. So if you've ever done carbon dating, which is basically you try to find out how old a fossil is, you can figure that out by the half-life. So there's a lot of applications for these functions, which is why I actually really like them. Exponential growth. So some patterns of growth and decay. I can even say and decay here. And decay. So some patterns of growth involve repeated multiplication of numbers greater than 1. And because those are repeated multiplications of numbers greater than 1 represented by an exponent, this type of growth is called exponential growth, right? So if you have repeated numbers multiplied by a number greater than 1, you'll notice that from 3 to the power of 1 to 3 to the power of 2, there's a big jump. Then 3 to the power of 3, there's a big jump. 3 to the power of 4, there's a big jump, right? So it grows very quickly. So the equation y equals abx models both exponential growth and decay, right? And A often represents the initial value, and we'll be discussing this a little bit further. So it's okay if you don't get it right now. Initial value, B represents the growth factor, right? How much it's going up by or how much it's decreasing by, and X represents the periods of growth, or like how long something takes to grow, or what round we're on, okay? The Y value is just the final amount of something. Okay, and honestly, the best way to do this is always to just do the math. So I'm just going to go back in here and I'm going to write our equation out for ourselves. So A is the initial value, B is our growth factor, and X is the number of rounds, right? So this is our final amount. This is our initial value. This is our growth factor. Right, and then this is our rounds or propagation or periods, whatever you may call it. Okay, so I like to go ahead and apply this to COVID. So before we even get started, there's this really great video by this man. He's an Oxford mathematician. He has a great YouTube channel on YouTube. His name is Dr. Tom Crawford. Right, he's a University of Oxford mathematician, so he's going to quickly talk to you about what exponential growth is and how it applies to COVID in particular. So I'm just going to play this.
Hello maths fans. Given the current global crisis, let's use this opportunity to do something positive and learn about exponential growth in the context of an
Sorry, I'm just going to make it so that it's a little bit larger.
symptoms, I go about my daily life, business as usual, and see exponential growth in the context of an epidemic. I'm going to run a pretend scenario where I have the disease, but because I have no symptoms, I go about my daily life, business as usual, and see where we end up. Current estimates from the World Health Organization for the virus COVID-19 give a reproductive number, R0 or R0, of around 3. So what this means in practice is that if I have the disease in this pretend scenario, then I would expect to infect around 3 other people. Now there are 4 of us that have the virus, but the good news is that I'm starting to feel a lot better. So whilst I'm no longer infectious, the 3 new people that I've passed the disease on to will then go on themselves to infect another 3 people each. Now 12 people have the virus. The original 3 that I infected, plus another 9 that they went on and infected themselves. And those 9 new infections will go on and each infect another 3 people. 36 people are now ill. We've got the 9 from 5 days previous, plus 27 new infections. It's getting pretty crowded. 108 people now have the virus. The 27 people who were infected 5 days earlier have each gone on to infect another 3 people, giving 81 new cases. It's fair to say that things are now definitely getting serious. 324 people now have the virus, which is far too many for me to fit on screen. Using data from 2018, 13% of the UK population...
All right, so I'm just going to close this. So obviously this doesn't take into consideration social distancing. It doesn't take into consideration that some people, when they start feeling sick, won't go out and meet people. It also doesn't take into consideration that after 14 days, you actually are no longer shedding the virus. But this is a really cool way for you to see how mathematical models can be used to understand spreads of disease and how they have been used to kind of figure out our projections, trying to figure out how we should go about opening things, and really like why diseases, especially like COVID, in this situation spread so fast. So we're actually going to we're going to make the model ourselves using the information that he had given us and the information given to us by who, and then we're going to go from there. So it says that a city begins with 10 cases of COVID-19. Each infected person interacts with about 3 people, 3 of who get the virus, right? Write an equation to represent the number of new cases, C, in the nth round. That just means that depending on, so if we say each round is 5 days, where like it takes 5 days for it to double and become something else, or 5 days for it to kind of like spread, like he was saying, every 5 days he figured out how much it spread. So we'll make this the nth round number of 5-day cycles, right? So you know how he was increasing by 5? So let's start with 10. So we know at round 0, like right at the beginning, there's only 10 cases. So the number of new cases is only 10. After the first round, so plus 5 days, right? You have 10 times 3 because now you've gone and talked to those 10 people have gone and talked to 3 people each. So we have 10 times 3 to the power of 1, right? Because it's just that, and that's going to give us 30. Right? So now we have 30 new cases. Then those 30 people have now gone and talked to 3 more people each. So we actually have to do 30 times 3, which is going to give us 90. Another way to look at this is just to do 10 times 3 times 3, because we did 10 times 3 the first time, and then those 30 people went and talked to somebody else. Right? And by that same logic, we want to go, okay, we have 90 people, so we have the people from the last round, right? And we're going to multiply those people by 3 as well. So now we have 270 people who have gotten the virus after 3 rounds. So that's about 15 days later, we have 270 cases, right? So now each round, right, the new number of cases is 10 times some power of 3. Notice how it's 10 to the power of 3 to the power of 1, 10 times 3 to the power of 2, 10 times 3 to the power of 3, and you can assume that the next one's going to be 10 times 3 to the power of 4, and so on and so forth. So if we wanted to write an equation for how this could work, we could say the number of new cases, right, is 10, which is the original number that we had, multiplied by 3, which is how much it increases by each time. We get 3 more people, 3 more people, 3 more people, to the power of n. And n represents the number of rounds, right? The number of plus 5 days that we're adding to this. Okay? So that would be our equation here, right? The 10 is the initial value. So let's just go back here and look at this. So see, C is the Y value, and that represents the final number of cases. That day, right? 10 is the initial number of cases we started with in this situation, right? So initial number of cases. 3 is the growth value. That's how much it goes up by each time, right? So I'm going to write that as growth value. And it's a integer number, so that we know it's going to be exponential growth, right? And then last but not least, n is the doubling time, or however long it takes, round of propagation. Or just, it's a fancier way of saying every 5-day period. Okay, so let's use this exponential growth equation from above, which is C equals 10, 3 to the power of n. Right, I'm just going to change the n back to black. Right, to solve how many new COVID cases you would expect after the 10th round of spread, which would be around roughly 50 days. Right, because it's going to be 5 plus 5 plus 5 plus 5 plus 5, which will be about 50 days. Right, so if it's going to be the 10th round of spread, we know that this value, n, is going to equal 10. Let's just write out our equation and substitute. We're looking for C, which is the number of cases. We have 10 to the power of 3 to the power 10 times 3 to the power of n. So it's going to be C 10 times 3 to the power of 10. Always do your exponent first, right? So we're going to do 3 to the power of 10, which is going to be 3 to the power of 10 is going to be 10 times 559,049, right? Multiply that by 10. We're going to get 590,490 cases. So, therefore, after 10 rounds of spread, we will have 590,490 cases. And yeah, some of these will be resolved. They won't all be active cases, but that's still quite a bit of a growth if you think about it, right? And if we were to graph that into decimals, you would see that. You would see that there's this huge spike. I'm just going to quickly go show you. Let's go here. Let's put in our model number. So it's going to be C. C is equal to 10, 3 to the power of x, or n, whatever you want to put there. And you'll see, starts off pretty small, right? We started off at 10 cases. We can't have negative cases, but we started off at 10 cases, but it goes up. Like, it just shoots up to the point where it's almost like a straight line, right? So you'll notice that it really expands really, really fast if you think about how fast these have been modeling and how fast they've been growing. And if you think about it, if we go and look at what the COVID curves look like, they do look something like this, like right at the beginning. Like, naturally, they're kind of starting to level off now. But at the beginning, they did look very like, woo, like super shot up. And that's why that is, because it's exponential growth. Okay. All right. So on the flip side, we have something called exponential decay. So growth means to grow rapidly. So decay means to decay rapidly. And in English, decay just means to kind of like wither away into nothing, right? So while repeated multiplication of numbers greater than 1 will produce increasing patterns, repeated multiplications of numbers less than 1, or fractions, right, will produce decreasing patterns, and that's called exponential decay. Because if you think about it, if you do 1 over 2 times 1 over 2, you get 1 over 4, and 1 over 4 is less than 1 over 2, so when you multiply fractions together, you actually decrease. Okay? And so, what happens is your exponential function for something that is decreasing, or for decay, will look something like this. Right? Where you'll start off with a lot and then you'll rapidly just kind of plummet down. Whereas with this one, remember, our COVID curves kind of look something like that. And where they're automatically rapidly increasing. So that's how you can know the difference between the two. If your graph is going up all of a sudden, right, it's increase. If it's coming down all of a sudden, it's decrease. Okay? So let's try doing a word problem with something like this as well. It's the same idea, right? So it says a rubber ball is dropped from a height of 200 centimeters and bounces several times. After each bounce, the ball rises to 80% of its previous height. Write an equation that represents the height of the ball, h, in centimeters after the nth ball. As a decimal, 80% is 0.8. So after each bounce, the height is about 0.8 times its previous height. So the first thing that we need to look for here is find out our equation. So if we go back and we look at our original equation, it was y equals a, b, x, where a represents the initial value. So let's go in and see, do we have the initial value information? Yeah, we do. It's 200. Right? Our base is our growth or decay factor. So let's go and try to find our growth or decay factor. Right? We know that it's decreasing by 0.8 each time. So our decay factor is going to be 8 or 0.8. And then we have the number of bounces, which is going to be our n variable. So if we're just going to use this basic equation to make the new one. And again, if you would like, I'm just going to pull this over here and I'll write out what each one represents. So this is final height. So I'm actually going to go change that over here. I'm going to change that to h. Right? That's our final height. This was our initial height. So then we have our initial height, and then we're going to look for our growth factor, which in this case was 0.8. And then this was like our interval or whatever, our period, which in this case was the number of bounces that impacted the height. Okay? So that is what that is going to be. That's what our height, or what our equation looks like, and how I figured out our equation. So I know the height is equal to 200. So I like to always just write in my equation first. N, where n represents the number of bounces, and we're trying to find it after the 5th bounce. So we know that n is going to be 5. So let's just go back in and figure out 200, 0.8 to the power of n, which is 5. Right? Always do the exponent first, so always do 0.8 to the power of 5. Again, I can just show you how to do that here. So I often just do it all together. So I like to do 200 times 0.8 all to the power of 5. And my answer is going to be 65.536. So I like to just write it in as 65.536. So I'll just write it as 5 centimeters. So therefore, after 5 bounces, and always write a therefore statement with word problems, after 5 bounces, the height is 65.5 centimeters. Okay, so now we're just going to go in and compare the two. So in general, when you're determining exponential growth versus decay, you're going to look at it this way. So exponential growth is always going to be growth that is rapidly increasing. So sorry about that. Rapidly increasing, going up this way, like that, right? It's going to have an equation like this where AF, right, or Y, whatever it might be, this is going to represent the final amount, right? The amount that you're looking at that time. AO is always going to represent the initial amount you start with. G is going to represent the growth factor, how much it's getting bigger by each time, right? How much it increases each time. And this has to be greater than 1. G must be greater than 1, right? And then last but not least, we have our N value, which in this situation, I'm going to write in this yellow marker, and that's going to be round of propagation, right? Like the amount of time something takes to happen, or double, or whatever it might be. So how many rounds you're doing of that thing, right? So it might be how many rounds of bouncing you're doing, how many rounds of COVID is spreading, how many rounds of doubling is happening, whatever it might be. On the flip side, you have exponential decay. So your graph for exponential decay will start off really high and then it'll kind of plummet down to the ground, right? It'll look something like that. You start off with, again, the final amount. So this is the same. The equation's pretty much the same. You have your final amount. You have your initial amount, which is the AO value. Right, you have your initial amount. The only difference here is your G value, or the amount it's growing, right, is going to be a decimal growth. So it's either a decimal or a fraction. Decimal or fraction. And it can also be called decaying value, decay value, decrease value. It's anything that's indicating that it's going down, right? And then last but not least, you have your N value, which is the number of rounds. Okay? So those are your two different equations. When we talk about exponential functions, the two things that we really focus on are exponential growth as a doubling time, and then exponential decay as half time. And the reason that is that a lot of different diseases and different like carbon dating practices use this function, right? So let's go over doubling time. Doubling time is basically just the time something takes to double in size. Could be a population, could be the spread of a disease, could be the number of bacteria in a colony, anything like that, right? When we look at doubling time, we use the equation AF equals A naught, or A0, to T over D. And in this situation, AF, same thing, represents the final amount. Right? A naught represents the initial amount. And I always like to look at it, it's A0, so it just means the initial amount when nothing's happened to it. Right? T represents the time that's passed. Time passed. And D in this situation is something new you're learning here, which is doubling time. And we'll tell you when something is doubling time. I'll tell you the doubling time is blah, blah, blah. So you'll put that as D. right? And the base of 2 basically just represents that something is doubling, right? So this base 2 indicates that something is doubling. So whenever I ask you on a test or a quiz, how do you know that something is doubling? You can just go and write like the base of this function. The number in the brackets is a 2. So I know that something is doubling. Cool. So let's move on. Let's just do an example together. So a bacterial culture begins with 10 bacteria. So we know our initial value, right, is going to be 10. Its growth can be modeled using the formula B equals 10 to T over 8, where B is the number of bacteria after T hours. What is the doubling time? Let's go and look at this equation and compare it to our original one. So we know AF is going to be the number of bacteria after our T hours. 10 was our initial amount. 2 is the base that represents that it's doubling. Then T is going to be the time that's passed. And then D is doubling time. Right? So what's our D value here? It's 8. So our D value is 8. So we know that the doubling time is 8 as it is the D value in the equation. And EQN just means equation. So then it asks us how much bacteria are present after 8 hours. So after 8 hours is the time that has passed, which we know is represented by the T value. So T is going to be equal to 8. So I'm just going to sub that in. Sub into formula. So let's go do that. We have B is equal to 10 times 2 T over 8, right? And let's just plug in our T value. 10, 2, 8 over 8. Always simplify your exponents first. So I'm left with T, 2, 8 divided by 8 is just 1. Then do the exponent next. 10, 2 to the power of 1 is just 2. So B is going to be 10 times 2, 20. So just make sure you follow BEDMAS. So B is going to be 20, and we know that B represents the number of bacteria. So therefore, there is 20 bacteria, or bacteria, I don't know, after 8 hours. So that's my answer. So with that being said, now you pause this video using the same formula, the same idea, find out how much bacteria are present after 16 hours, and how does this relate it to the doubling time. So hopefully you pause the video. Let's go through it. How much bacteria are present after 16 hours? So 16 hours is the time that has passed. Right? So we know we can sub 16 for T. So let's do that. B is equal to 10 times 2 T over 8. B is equal to 10 times 2. T is going to be 16 over 8. Always do your exponent first, so simplify that. So 10, 2. 16 divided by 8 is just 2. B is equal to 10. Always do the squared first. 2 squared is 4. B is equal to 10 times 40. So I have 40 bacteria now. Therefore, after 16 hours, So how does this relate to the doubling time, right? And if you think about it, 16 hours, if the bacteria doubles every 8 hours, 16 hours means that they have now doubled not once, but twice. So you've doubled 2 times. So you've done 2 propagation rounds, right? Which makes sense because if you started off with 20, or if you started off with 10, so let's say we had 10 and 10, and after one round, this 10, or we started off with 10 rather, after 10, one round, we made 20, right? Because both of them doubled. Then we made 10 more for each, right? You were left with 40. So that's how this works. So you start off with 10. Those 10 multiply into 2 separate groups of 10s. They have their babies. They do whatever they need to do. Each person has a baby, 10, 10, right? And then each of those couples has another one. So then we have 40 left at the end. So in theory, with this being said, each of these 10 will also double. So after our third round, which will be after 16, 8 plus 8 plus 8, which will be 24, right? We'll have 1, 2, 3, 4, 5, 6, 7, 8, 80 of them, and so on and so forth. That's how that would work. And I'm just going to erase this. But that's if it asks you how does that happen, this is the reason why. So on the flip side, we have something called half-life, which is the time it takes for a quantity to decay or be reduced to half its original amount. So say I had 30 pounds of chocolate, right? And its half-life is I eat it every 15 minutes. I eat 15 pounds of chocolate, right? After half an hour, I'll only have 15 pounds of chocolate left, or 15 grams, whatever I started with, right? So I'll have half the original amount. So if I started with 30 grams, I'll have 15 grams left, and then I'll have half of the 15 left, which is 7.5. Then I'll have half of the 7.5 left, and you'll kind of just keep halving. You won't ever get to 0. You'll just get to very, very close to 0. Okay? So half-life is very similar formula, except now instead of D, you have H. This represents the half-life of something, how long it takes for that one thing to go to half of the amount, right? T is still the time that has passed, and I think I actually put that in the pink, so I will keep the same colors. So this is time that's passed, right? AF is still the final amount, and AO is still the initial amount. And now we have 1 over 2, right? This 1 over 2 represents the half-life, right? The base of 1 over 2. So when you see that it's a half, you automatically know that it's half-life. And I remember that because it's half. So that means it has to represent half-life, and it can't be 2 because you're not doubling here. Okay? So let's do an example. Always easier to do an example. So let's go through this. So the half-life of iodine is, our half-life of iodine 131. 131 is just the name of the element. Don't worry about it. Every element has like a radioactive name. It's not important. It's not an important number either. It's just there for scientific purposes. So the half-life of iodine 131, an element used in nuclear medical procedures, is 8 days. The remaining amount of iodine is modeled by the formula I equals IO half N over 8. Same formula format. This is just AF, this is just AO, and this is just T over H, right? You just need to be able to see that formula in every new formula I give you. Where I is the number of the amount of iodine, the final amount, IO is the initial amount, and N is the number of days, right? Determine the following about the amount of iodine 131 in the following situations. So, how much am I going to have if I started off with 50 grams of iodine after 8 days? So let's just go in, write our formulas. I is equal to 50, which is, let's just go in and write, sorry, or I not. So I naught, right? Half n over 8, right? So a few things I need to substitute in here. I don't know what I is, so I don't need to put that in. I know IO, or the initial amount, is 50 grams. And I know that my n value is going to be 8, right? Because it says after 8 days, and n represents how many days have passed. So I is equal to 50 half 8 over 8, right? Always go simplify your exponent first. So you have 50, 1 half. 8 divided by 8 is just 1. I equals 50. Then do your exponent. So we have 1 half to the power of 1, which we know anything to the power of 1 is just itself. And then we're left with 50 multiplied by a half, which we know is 25. So I know that after 8 days, I will have 25 grams left of iodine. And just write that in. Make sure you always have your units as well. So after 8 days, I'll have 25 grams of the original 50 left over. And that's our answer. So you try and do B by yourself, and then we have one more example here, and then we can be done this lesson. So hopefully you pause the video and you tried that on your own, right? Let's move forward. So you have 50 grams after 12 days, right? And it says, so you started off with 50 grams. So our IO, you're going to use the same idea. Our IO is 50. Our N is going to be 12 this time, right? We're still using the same formula. So we're going to use I equals IO, 1 half N over 8, right? I, we don't know what that is. IO, we know is 50. That's how much we started off with. Half 12 days is how much time has passed over 8. So always go in and deal with simplifying your exponent first. 12 divided by 8 is 1.5. Yes, in this situation, you can have a decimal as your fraction. So let's just go into our calculator, right? And I'm going to show you how to put this in. So you can just do this, and then you use your fraction button here and write 1 over 2, bracket, always bracket close it, you won't get the right answer, to the power of 1.5, and you're going to get 0.35355, right? And you're just going to say, okay, enter, right? And I'm going to multiply my answer by my initial value, which was, I think I started off with 50 grams, 50. So my answer is going to be 17.677669, right? So I'm going to write it as I is equal to 17.67 grams. So after 12 days, I'll have 17.67 grams left over. So therefore, perfect. So now that you know how to do both exponential decay and exponential growth questions, I want you to try doing number 1 all by yourself completely. So pause the video here, go through it by yourself, try it on your own, and then we can take it up together. So when when you unpause this video, I'll be here to take it up with you. All right, so hopefully you actually paused the video, went through it. If you didn't, please pause it again. You won't learn anything if you don't pause the video and go through the stuff by yourself. Other than that, I am going to take it up with you now. So it says a population of ants can be modeled using this equation, right? Where AF is the current population of ants, AO is the initial population of ants, and T is the time in hours. Does this equation represent doubling or half-life? Explain how you know. So if I go in here, I'm going to look at my base. My base is 2. Therefore, this equation represents doubling time, because I know that if the number in the bracket is a 2, the base is 2, which represents doubling. Or exponential growth. Right? It's increasing by a factor of 2 each time, so it's doubling. What is the doubling time or half-life time of this population? So we know it's doubling time, right? And if I look at my equation, I'm just going to go and find the D value, which in this situation is 10, right? So the doubling time, I'm just going to write dt, is 10, right? Because it's the D value. And it helps to just have a copy of the of this equation, like this, beside you. Like I always keep this beside me, or like this beside me. Right, a copy of those questions, of those labeled formulas. So if a sample contains 100 ants, how many will there be after 10 hours? So let's go in and use our formula and fill it out. So I have AF is equal to A naught times 2 10 over T, right? Let's go label in what each of these is. 100 ants represents AO, right? That's how much I'm starting off with. And the 10 hours represents T. So let's go sub in those numbers. So I have AF is equal to 100 ants to start with, T, which is going to be 10 hours, over 10. So AF is equal to 100. 10 divided by 10 is just 1, so it's 2 to the power of 1, right? 100, we're going to do our exponent now. 2 to the power of 1 is just 2. So our formula is going to say it's going to give me 200. That means that after 10 hours, I'm going to have 200 ants. This one's easy. We've been doing this so many times. Next one's a little bit tricky. So if a sample contains 512 ants after 100 hours, how many ants were there to start with? So now instead of looking for AF, what we're actually looking for is AO, right? So again, same idea. You just need to know what the question is asking, right? It's asking us how much should we have to start with. So we're still using the same formula. Oops, I'm just going to go fix that. T over 10, right? We still have a T value, which is our 100 hours. Except now we have an AF value as well. Our AF value is 512,000. So let's go substitute our stuff in. So we have 512,000 is equal to AO, which we're looking for, to 100 divided by 10. Divided by 10. So let's go. We're going to solve this the same way. So first things first, let's do our 100 divided by 10. It's going to give us, we're just going to rewrite our number in here. So we have AO, right? Let's deal with our exponent first. So it's going to be 2 to the power of 100 divided by 10, 2 to the power of 10, right? Now let's deal with that exponent. So AO times 2 to the power of 10 is going to be 1024, right? I'm just going to rewrite this. Actually, let's leave it. So now I know I want to get the AO by itself, so I want to get rid of this 1024. And since they're multiplying, I'm just going to do the opposite and divide it on this side and divide it on this side. So now I'm left with 512,000 divided by 1024, which is going to give me 500, is equal to A naught. So I know that my initial value, the initial amount of ants, was 500. And so you're basically just doing the same thing except backwards. Okay? And that's it. That's it for the lesson. See you later.